Imagine standing at the edge of the universe, staring into the void where space and time themselves seem to unravel. What holds it all together? What invisible threads weave the fabric of reality? This isn't just science fiction, it's the burning question at the heart of quantum gravity, one of the most profound mysteries in all of physics. Even after decades of research, the universe refuses to give up its deepest secrets easily. The clash between the colossal scales of general relativity and the minuscule world of quantum mechanics leaves us with a paradox so baffling, it keeps physicists awake at night. And today, we're diving headfirst into that enigma, exploring 30 mind-bending theories that attempt to bridge the gap between these two titans of physics. Think about it for a second. Gravity, the force that keeps your feet on the ground and planets in orbit, is the only fundamental force that stubbornly resists being squeezed into the quantum framework. We've tamed electromagnetism, the strong and weak nuclear forces, but gravity, it's the wild card, the one that refuses to play by the same rules, and that's what makes quantum gravity such an electrifying puzzle. If we crack it, we might unlock the ultimate blueprint of reality itself, revealing how black holes truly behave, what happened in the first moments of the Big Bang, even whether parallel universes could exist. The stakes couldn't be higher, so why haven't we figured it out yet? Well, as you're about to see, the answers we've come up with are as strange as they are brilliant. From loop quantum gravity's tiny, woven space-time threads to string theories, vibrating cosmic strings, each idea pushes the boundaries of what we thought was possible. Some theories suggest space itself is pixelated, like a cosmic digital screen. Others argue time might not even exist at the most fundamental level. And then there are the truly wild contenders, like holographic universes, where our 3D reality is just a shadow of a higher dimensional world. Buckle up, because we're about to journey through the most daring, imaginative, and downright astonishing attempts to solve the quantum gravity riddle, one mind-blowing theory at a time. Let's start with loop quantum gravity, a theory that turns our intuition about space and time completely on its head. Picture the universe not as a smooth, continuous fabric, as Einstein's general relativity suggests, but as a sprawling network of tiny, woven loops. These loops, like the threads of an impossibly intricate cosmic tapestry, are the building blocks of reality itself. The theory emerged in the late 20th century as a bold attempt to reconcile gravity with quantum mechanics, and one of its leading voices, physicist Carlo Rovelli, describes it as space-time finally getting the atomic treatment. At its core, loop quantum gravity proposes that space isn't infinitely divisible, it's made of discrete, indivisible chunks or quanta, woven together by these loops. Think of it like pixels on a screen, but instead of flat squares, you've got tiny, vibrating rings that define the very structure of space and time. This means there's a smallest possible unit of space, a limit to how finely you can divide it, no infinite smoothness, no endless shrinking down to zero. It's a radical departure from Einstein's vision, where space-time bends and curves like a rubber sheet. Here, space-time is more like a mesh with gaps and connections that give rise to gravity itself. The implications are staggering. If loop quantum gravity is correct, even the vacuum of empty space isn't truly empty. It's a seething network of these loops constantly interacting. And when matter or energy enters the picture, it warps this network, creating what we perceive as gravity. Suddenly, black holes and the Big Bang start looking very different. Near a black hole singularity, for instance, the loops might resist being crushed into oblivion, preventing the infinite densities that classical physics predicts. But the theory isn't without its challenges. For one, it's notoriously difficult to test. These loops are unimaginably small, far beyond what any particle collider can probe. And while it beautifully quantifies space, it struggles to fully incorporate time in the same way. Yet, for all its hurdles, loop quantum gravity remains one of the most compelling frameworks for a quantum theory of gravity. It doesn't rely on extra dimensions or hidden universes, just the sheer, elegant geometry of space itself. And that's what makes it so tantalizing. In a cosmos full of mysteries, it dares to suggest that the answers might be written in the very fabric of reality, one tiny loop at a time. Now let's shift our gaze to string theory, a framework so ambitious it doesn't just aim to explain quantum gravity. It dares to be the so-called theory of everything. If loop quantum gravity imagines space as a woven tapestry, string theory takes it even further, suggesting that the fundamental building blocks of reality aren't particles at all, but tiny, vibrating strings. Picture an unimaginably small cosmic violin, its strings resonating at different frequencies to produce every particle and force in the universe. Electrons, quarks, even the elusive graviton, they're all just different notes played by these microscopic strings. What makes this idea so compelling is how effortlessly it marries gravity with quantum mechanics. In string theory's universe, gravity isn't an outsider. It's just another vibration, another harmonic in the grand symphony of physics. Unlike the particle-based approaches that stumble when gravity enters the picture, strings handle it with elegance. Every interaction, every force emerges from their dance. And here's the kicker: string theory doesn't stop at 4 dimensions. To make the math work, it demands a staggering 10 or even 11 dimensions, curled up so tightly we'd never notice them in everyday life. It's as if we've been living in a flat, 2-dimensional world, completely oblivious to the depth all around us. Yet for all its mathematical beauty, string theory comes with a glaring caveat: we have no experimental proof. These strings are thought to be so small that detecting them directly would require energies far beyond what our most powerful particle colliders can muster. Critics argue that without testable predictions, string theory veers closer to philosophy than physics. But its defenders counter by pointing to its sheer explanatory power, how it naturally unites all fundamental forces, how it elegantly sidesteps the infinities that plague other quantum gravity models. Then there's the tantalizing possibility of supersymmetry, a cornerstone of many string theories that predicts a hidden twin for every known particle waiting to be discovered. The debate around string theory is as fiery as the theory itself is complex. Some hail it as the only viable path to a unified physics, while others dismiss it as an untestable mathematical mirage. But whether it's the ultimate theory or a beautiful dead end, one thing's certain: string theory has reshaped how we think about reality's deepest layers. It challenges us to imagine a cosmos where the familiar laws of physics are just the surface ripples of something far richer, far stranger, a universe humming with invisible strings, playing the tune of existence itself. What if space-time wasn't a smooth fabric or a web of loops, but a mosaic of tiny, rigid triangles? That's the bold premise of causal dynamical triangulations, a theory so visually striking it feels like geometry brought to life. Picture slicing the universe into microscopic triangular chunks, tetrahedrons. To be precise, each one a building block of reality. Unlike string theory's elegant vibrations or loop quantum gravity's woven threads, this approach treats space-time like a cosmic Lego set where every piece snaps together under strict rules. And here's the twist: these triangles don't just sit there. They evolve step by step in a way that preserves causality, meaning no event can influence another faster than light allows. It's relativity's speed limit baked into the very structure of space-time. The brilliance of this model lies in its computational power. By simulating these triangulations on supercomputers, physicists can watch virtual universes emerge from the chaos. Start with a random pile of triangles, let them interact under the theory's rules, and something remarkable happens. A 4-dimensional universe resembling ours crystallizes out of the noise. No manual sculpting, no hidden assumptions, just simple geometry giving birth to the familiar fabric of space and time. It's like witnessing the universe self-assemble one triangle at a time. But the real magic is how causal dynamical triangulations sidestep the nightmare of singularities, those infinitely dense points where Einstein's equations break down. In this framework, space-time can't crumple into a true singularity because the triangles act like a safety net. They impose a minimum scale, a smallest possible unit of curvature. So when matter collapses under gravity, like in a black hole, it reaches a point where the triangles simply can't compress further. The result, a bounce, not a breakdown. No infinite densities, no lost information, just a cosmic reboot that hints at resolutions to some of physics' fiercest paradoxes. Of course, no theory is flawless. Critics point out that while the simulations are mesmerizing, they're still approximations, a simplified playground compared to the messy richness of reality. Unlike its peers, causal dynamical triangulations hasn't yet produced testable predictions we can probe in a lab. Yet its elegance is undeniable. It doesn't need extra dimensions or hidden universes to tame gravity, just triangles, causality, and a dash of computational daring. In a field where complexity often clouds clarity, this theory reminds us that sometimes the deepest truths hide in the simplest shapes. What if gravity wasn't the unruly rebel of the quantum world, but a force that eventually settles down when pushed to its limits? That's the surprising promise of asymptotic safety, a theory that flips the script on quantum gravity by suggesting gravity might finally play nice at ultra-high energies. Picture a wild river raging through a canyon, chaotic, unpredictable, but as you follow it upstream, something unexpected happens. The currents smooth out, the turbulence fades, and the water flows with perfect, predictable clarity. That's the essence of asymptotic safety. Gravity's quantum chaos might vanish when energy scales become extreme, revealing a hidden order beneath the storm. This idea hinges on a concept called renormalization, a mathematical tool physicists use to tame infinities that plague quantum theories. Usually, gravity's quantum version spews out infinite, nonsensical answers when particles interact at tiny scales. But asymptotic safety proposes a loophole. What if gravity's strength, its so-called coupling constant, doesn't spiral out of control at high energies? Instead, it could reach a fixed point, a kind of quantum equilibrium where calculations stay finite and meaningful. Imagine tightening a loose guitar string until it hits the perfect pitch. No matter how much you twist further, the note stays clean. That's the dream here, gravity's equations stabilizing rather than exploding, making it as manageable as electromagnetism or the nuclear forces. The theory's appeal lies in its minimalist elegance. Unlike string theory's extra dimensions or loop quantum gravity's space-time loops, asymptotic safety doesn't demand a radical overhaul of reality. It works within the familiar framework of quantum field theory, the same toolkit used for other forces. Just tweak gravity's behavior at extreme scales and suddenly, black hole singularities or the Big Bang's fiery dawn become calculable, not catastrophic. Some simulations even hint at this fixed point existing, teasing the possibility that Einstein's theory and quantum mechanics might shake hands after all. Yet for all its promise, asymptotic safety remains a contentious bet. Critics argue that proving this fixed point exists mathematically or experimentally is like chasing a ghost. The energy scales involved are so far beyond our reach that testing it directly might be impossible. But its supporters counter with a compelling thought. If true, asymptotic safety could be the universe's quiet surrender, a sign that even gravity, the last wild force, eventually bows to the rules of quantum order. And that's a revelation worth chasing, no matter how elusive. What if gravity isn't a fundamental force at all, but something that simply emerges from the chaotic dance of quantum information? That's the startling claim at the heart of emergent gravity, a theory pioneered by physicist Eric Verlin that flips everything we thought we knew about gravity upside down. Forget bending space-time or vibrating strings. Verland suggests gravity might just be a side effect, a cosmic illusion born from the way quantum particles entangle and interact. It's as if we've been studying the ripples on a pond without realizing they're just echoes of something deeper happening beneath the surface. To grasp this, think about temperature. We experience it every day, but it's not some intrinsic property of matter. It's just the average jiggling of countless molecules. Similarly, Verland argues gravity could be a kind of statistical effect arising from the way quantum bits of information rearrange themselves. The math behind it draws surprising parallels to thermodynamics, the science of heat and energy flow. Just as heat emerges from microscopic chaos, gravity might emerge from the quantum entanglement of space itself. Picture a crowd at a concert. No single person dictates the movement, but the collective push and pull creates waves that ripple outward. Gravity, in this view, is the crowd's motion, not a force but a pattern. The theory's boldest implication: dark matter might not exist. Instead of invoking invisible particles to explain galaxies' strange rotations, Verland's equations suggest gravity itself behaves differently on cosmic scales due to the way quantum information fills space. It's a jaw-dropping idea, one that could erase one of astronomy's biggest mysteries with a single conceptual shift. But not everyone's convinced. Traditionalists argue that without direct experimental proof, emergent gravity remains a captivating thought experiment. After all, how do you test something that redefines the very nature of a force we've measured for centuries? Yet the theory's elegance keeps it in the game. It doesn't require extra dimensions or untested particles, just a radical rethinking of how information shapes reality. And in a field where breakthroughs often come from questioning the obvious, Verland's gamble reminds us that sometimes the most fundamental truths are the ones we haven't thought to question yet. Whether emergent gravity ultimately holds up or not, it's a thrilling reminder that the universe still has surprises up its sleeve, and that gravity, the force we thought we knew, might be hiding its true nature in plain sight. Black holes aren't just cosmic vacuum cleaners, they're laboratories for the most extreme physics imaginable. And when it comes to quantum gravity, they might hold the keys to unlocking the universe's deepest secrets. Enter black hole thermodynamics, a framework that stitches together gravity, quantum mechanics, and even the laws of heat and energy into one startling picture. At the heart of it all is Hawking radiation, the mind-bending discovery that black holes aren't entirely black. They glow, they leak, and in doing so, they might reveal how space-time itself is woven from quantum threads. Stephen Hawking's breakthrough was this: if you zoom in close enough to a black hole's edge, quantum fluctuations tear particle-antiparticle pairs from the vacuum. Normally, these pairs annihilate instantly, but near the event horizon, one particle falls in while the other escapes, stealing a tiny bit of the black hole's mass. Over eons, this slow drip of radiation causes the black hole to evaporate, leaving behind a puzzle. Where does all the information about what fell in go? Quantum mechanics says information can't be destroyed, but black holes seem to erase it, unless the information isn't lost at all. That's where the holographic principle comes in. Imagine taking every single bit of data that ever crossed a black hole's horizon and encoding it on its surface like a cosmic hard drive. Instead of vanishing into the singularity, the information gets smeared across the event horizon in quantum pixels so fine, they redefine what we think of as space. This isn't just a wild guess. The math suggests a black hole's entropy, its hidden information, scales with its surface area, not its volume. It's as if the 3D universe we experience is just a projection of a 2D code written on the boundaries of reality. But the implications go even further. If black holes can store information holographically, maybe the entire universe does the same. Some theories propose that our cosmos is like a black hole's interior, a vast three-dimensional illusion built from quantum data painted on some distant, invisible surface. It's a dizzying thought. The stars, galaxies, even your own hands might be shadows cast by bits of information we can't see. Of course, not everyone's convinced. Critics argue that without direct evidence of Hawking radiation or a way to probe a black hole's quantum surface, these ideas remain speculative, but the stakes are too high to ignore. If black hole thermodynamics is right, it means space-time isn't the fundamental fabric of reality. It's something that emerges from a deeper quantum layer we're only beginning to glimpse. And that changes everything, from the fate of information in the cosmos to the very nature of existence. Black holes aren't just swallowing light. They might be shining it on the path to quantum gravity itself. Picture the universe not as a vast three-dimensional expanse, but as an intricate cosmic illusion, a hologram. The holographic principle suggests everything we see, touch, and experience might just be a shimmering projection of information encoded on a distant two-dimensional surface. It's as if reality is a movie screen, and we're the characters who have forgotten we're made of pixels. This idea didn't emerge from science fiction, but from the cold, hard math of black holes and string theory, forcing us to confront a dizzying possibility. Depth itself could be a grand cosmic trick. The seeds of this theory were planted in the study of black holes. When physicists calculated the entropy, the hidden information inside a black hole, they stumbled on something bizarre. Instead of scaling with the volume as you'd expect, it matched the area of the event horizon. It was like discovering a library's entire collection could be written on the covers of its books. This led to a radical question. What if all the information about what's inside a black hole is somehow smeared across its surface? And if that's true for black holes, could it be true for the universe itself? String theory supercharged this idea. In certain versions of the framework, a universe with gravity in 5 dimensions can be perfectly described by a quantum theory without gravity operating on its 4-dimensional boundary. It's as if the 3D world we inhabit is just a shadow cast by interactions happening on a higher dimensional edge we can't perceive. Imagine a sculptor chiseling a statue. The real artistry isn't in the marble but in the sculptor's mind. Similarly, the holographic principle implies our 3D reality might be the marble, while the true artistry happens on a distant, immaterial surface. But how could this possibly work? Think of a credit card hologram tilted, and the flat sticker projects a 3D image. The holographic universe operates on a similar principle, but instead of light, it's quantum information doing the projecting. Every particle, every force, even the passage of time could emerge from a swirling dance of data written on the universe's outermost shell. It's a concept that rewrites the meaning of here and there. The screen you're staring at right now, your hands, the air you breathe, none of it might be fundamentally local. It could all be a translation of something happening far away in a realm we'll never see. Skeptics argue the holographic principle is untestable, a beautiful idea floating in a sea of speculation, yet it's hard to ignore its explanatory power. It dissolves the infamous black hole information paradox by suggesting nothing ever truly falls into a singularity. It's just repackaged on the horizon. It also hints at a solution to quantum gravity, showing how space-time could emerge from entangled quantum bits, like a 3D mirage rising from a 2D desert. Whether the holographic principle holds up or not, it's a staggering reminder of how little we truly grasp about reality's architecture. The universe might not be a stage we stand on, but a performance, one where the actors, the set, and even the script are woven from something far stranger, far simpler, lurking just beyond the edges of perception. And that's a mystery worth falling into. What if the smooth, predictable space-time we take for granted is just an illusion, a blurry average of something far stranger at the tiniest scales? Non-commutative geometry dares to suggest exactly that, painting a picture of reality where the very coordinates of space and time become fuzzy, unpredictable, and fundamentally reshuffled. Imagine trying to pinpoint a location on a map, only to find that north and west stop being reliable directions when you zoom in too close. This isn't just navigational chaos, it's a radical reimagining of the universe's blueprint, one where the fabric of reality itself becomes a seething quantum foam at the Planck scale. At the heart of this theory lies a mathematical twist, the idea that space-time coordinates no longer commute. In everyday life, order doesn't matter. Telling someone to move 5 steps north, then 3 steps east gets you to the same spot as 3 east, then 5 north. But in non-commutative geometry, this neat symmetry breaks down. Multiply 2 numbers representing positions, and the result changes depending on which one you put first. It's as if the universe has a hidden rulebook where the act of measurement distorts the very thing you're trying to measure. And this isn't just mathematical abstraction. At scales a billion trillion times smaller than an atom, space-time might dissolve into a frothing sea of unpredictability, where exact locations lose all meaning. The architect of this vision, mathematician Alain Connes, didn't set out to upend physics. His work began in pure mathematics, exploring exotic algebraic structures where numbers refused to play by classical rules. But when physicists grappling with quantum gravity stumbled upon these same mathematical patterns, the implications became impossible to ignore. Connes' framework suggests that what we call space might emerge from something deeper, a web of abstract relationships where geometry is no longer about points and distances, but about the dance of quantum operators. Picture a grand symphony where the notes themselves define the stage, and the stage changes depending on how you listen. The consequences are staggering. If space-time is non-commutative at its core, then the smooth continuum Einstein described is just a low-resolution snapshot. Zoom in far enough, and the universe starts resembling a Monet painting orderly from afar, but a riot of disconnected brushstrokes up close. This could resolve some of quantum gravity's thorniest puzzles, like the infinite energies that plague other theories. If measurements blur at the tiniest scales, those infinities might simply vanish, smoothed away by the inherent fuzziness of reality itself. Yet for all its elegance, non-commutative geometry raises existential questions. How does our crisp, classical world emerge from such quantum chaos? And can we ever test a theory where the very tools of observation, space and time become unreliable? Some researchers hope that subtle imprints of this quantum foam might linger in high-energy cosmic rays or the afterglow of the Big Bang, waiting to be decoded. Others see it as a mathematical Rosetta Stone, bridging the language of quantum mechanics with the geometry of the cosmos. Whether it's the final answer or just another clue, non-commutative geometry forces us to confront a humbling truth. The universe might not just be stranger than we imagine, but stranger than we can imagine. And in that uncertainty lies the thrill of the hunt, one where the map of reality is still being drawn, one non-commuting step at a time. Picture the universe not as a smooth continuum, but as a vast cosmic ledger, a collection of discrete, individual events connected by a strict web of cause and effect. This is the essence of causal set theory, a radical approach to quantum gravity that trades Einstein's elegant curves for something far more granular. Forget bending space-time. Here, reality is built from finite, indivisible moments, each one linked to others in an unbreakable chain of causality. It's as if the universe is a meticulously plotted novel, where every event is a sentence that can only follow the ones before it. The brilliance of causal sets lies in their simplicity. While other theories grapple with extra dimensions, vibrating strings, or fuzzy geometries, this framework strips everything down to 2 basic ingredients: discrete events and the causal relationships between them. Imagine tossing a handful of sand onto a table. Each grain represents an event, a tick of the cosmic clock. and the way they land defines which grains influence others. Some sit to the left, others to the right, but crucially, none can affect grains that came before them. This strict ordering eliminates the infinities that plague traditional physics, like the nonsensical singularities at the heart of black holes. In a causal set, there's no such thing as infinite density because there's no infinitely small point, just a finite sequence of steps, like a cosmic staircase that never crumbles. One of the theory's most startling implications, time might be more fundamental than space. In causal sets, the relationships between events, the before and after, come first, and space emerges as a secondary effect. Think of it like a social network. The connections between people define the structure, not the physical distance between them. Similarly, the universe's geometry isn't handed down from on high. It's woven from the causal threads tying events together. This flips Einstein's space-time on its head, suggesting that what we perceive as a unified fabric is really just a shadow cast by deeper causal logic. But how do we get from this sparse network of events to the rich, 3D world we experience? That's where the magic of sprinkling comes in. Theorists use probabilistic methods to scatter events into a structure that, when zoomed out, approximates the smooth space-time of general relativity. It's like pointillism in art. Up close, you see individual dots, but step back and a coherent image emerges. The challenge, of course, is proving this matches reality. Causal sets make a bold prediction. Space-time should appear subtly grainy at the tiniest scales, a signature that might one day be detected in high-precision experiments or the faint whispers of quantum gravity waves. For all its elegance, causal set theory isn't without skeptics. Some argue its minimalist approach is too sparse, leaving out key features of quantum mechanics or struggling to reproduce Einstein's equations exactly. Yet its proponents counter with a compelling point. In a field crowded with complex abstractions, sometimes the most profound insights come from the simplest assumptions. By starting with nothing but causality and discreteness, this framework reminds us that the universe's deepest truths might not lie in elaborate constructs, but in the quiet, relentless logic of cause and effect, one irreducible event at a time. What if the tangled equations of quantum gravity could be unraveled by looking at space-time through an entirely new lens? One where points aren't points at all, but intricate relationships between swirling, hyperdimensional objects. That's the visionary promise of twistor theory, a framework forged by physicist and Nobel laureate Roger Penrose that trades traditional coordinates for something far more elegant. Imagine trying to navigate a city not by street addresses, but by the way light rays crisscross between buildings. Twistor theory does something similarly radical. It replaces the familiar dots on the space-time map with geometric dances between Twistor's abstract mathematical entities that encode both position and momentum in a single, fluid stroke. At its core, twistor theory flips the script on how we describe reality. Instead of starting with space-time and forcing quantum mechanics to fit, Penrose's approach builds space-time from quantum foundations. Each twistor represents a light ray's entire history, its direction, energy, even its quantum spin, woven into a complex number living in a higher dimensional space. When these twistors interact, their intersections create the familiar fabric of space and time we perceive. It's like discovering that the pixels on your screen aren't static dots, but tiny vortices whose interactions generate the image. Suddenly, the stubborn clash between Einstein's smooth geometry and quantum uncertainty starts to soften because twistors naturally blend both worlds. The math behind this is breathtakingly concise. Where traditional quantum gravity theories drown in infinite corrections and unruly terms, twistor equations often simplify dramatically. For example, certain particle scattering calculations, a nightmare in standard frameworks, become almost trivial when recast in twistor language. Penrose himself likened it to finding the right key for a lock. The equations click into place with fewer steps, fewer contradictions, and a haunting beauty that suggests deeper truth. Even string theorists have borrowed twister techniques to tame their own mathematical beasts, proving its versatility. But the theory's boldest claim is that space-time itself might be emergent, a secondary effect of deeper twister relationships. Picture a lake's surface. The waves you see aren't fundamental. They're born from the water's hidden molecular dances. Similarly, twisters could be the deeper layer, with space-time as the ripple. This could explain why quantum gravity resists traditional approaches. We've been studying the waves, not the water. Yet for all its elegance, twister theory remains a work in progress. Critics point out it hasn't yet reproduced all of general relativity or definitively predicted new phenomena. Others argue its abstract math, while beautiful, is like a locked safe without a clear combination. But recent breakthroughs, like the discovery of amplituhedrons, geometric shapes that simplify particle interactions using twister-inspired logic, hint at untapped potential. And in a field where progress often hinges on radical reframing, Penrose's twisters remind us that sometimes the key to reality's deepest mysteries isn't more complexity, but a shift in perspective, one where space-time isn't the stage but the dance itself. If loop quantum gravity paints space-time as a network of woven threads, group field theory takes that vision and sets it boiling. Picture the universe not as a static tapestry, but as a seething cauldron of quantum foam, each bubble a fluctuating knot of group fields, constantly merging, splitting, and rewriting the rules of geometry itself. This isn't just abstract math. It's a radical reimagining of how the cosmos might stitch itself together at the smallest scales, where space and time lose their sharp edges and dissolve into a dynamic, frothing dance. At its core, group field theory builds on loop quantum gravity's foundation but cranks up the complexity. Instead of isolated loops, it treats space-time as a vast, interacting gas of these loops, a quantum foam where each bubble carries the imprint of a symmetry group, a mathematical fingerprint that dictates how it can twist, stretch, or fuse with its neighbors. Think of it like a crowd at a concert. Loop quantum gravity studies individual dancers, while group field theory captures the wave they create together, an emergent rhythm that transcends any single participant. The equations governing this foam are fiendishly complex, but their promise is tantalizing. They could reveal how the smooth space-time of general relativity crystallizes from the chaos of the quantum world. Where this gets mind-bending is in cosmology. Group field theory suggests that the Big Bang might not have been a singular explosion from nothing, but a phase transition, a cosmic reshuffling of this quantum foam, like water freezing into ice. In this view, the universe's birth wasn't a violent rupture, but a reconfiguration of geometric relationships, with space-time itself condensing out of a hotter, denser froth. Simulations based on these ideas show virtual universes popping into existence, not from a point, but from a bubbling quantum substrate, hinting at answers to why our cosmos has the structure it does. Visualizing this foam is no easy feat, but theorists have tried. Some models depict it as a kaleidoscopic swarm of tetrahedrons, constantly flipping inside out. Others borrow from fluid dynamics, showing space-time as a turbulent ocean where waves and vortices collide. What's striking is how these visualizations echo old ideas of space-time foam from mid-century physicists, except now they're grounded in rigorous math, not just metaphor. Yet challenges remain. Group field theory's equations are so intricate that even supercomputers groan under their weight, and experimental tests feel light years away. Critics argue it's more math than physics until we find tangible evidence, but its proponents counter with a thrilling possibility. If space-time really is a quantum foam, the echoes of its bubbling might linger in the faintest light from the early universe, or in the way particles wobble at extreme energies. Whether it's the final word or just another step, group field theory dares us to rethink reality's fabric, not as something handed down from on high, but as a living, churning thing born from the ceaseless dance of its tiniest parts. And in that dance, we might finally find the rhythm of quantum gravity. What if the smooth, orderly space-time we take for granted was born from cosmic chaos, a frenzied, structureless graph that somehow froze into the universe we recognize today? That's the startling premise of quantum gravity, a theory that reimagines the early cosmos as a seething network of disconnected nodes, more like a shattered mirror than a cohesive fabric. Imagine tossing a handful of iron filings onto a table. At first, they're scattered randomly, but bring a magnet close, and suddenly they snap into organized lines. Quantum gravity suggests something eerily similar happened to reality itself in the moments after the Big Bang, a phase transition where the universe went from wild incoherence to structured geometry in a flash. The theory's name is a playful nod to its central idea: graphity blends graph with gravity, hinting at how the structure of space might emerge from a primordial mathematical graph. Picture this graph as a vast, hyperdimensional web where each point is connected to others by links representing potential relationships. In the beginning, these links are entirely random, like a game of quantum pinball where every node interacts with every other in a dizzying, lawless frenzy. But as the universe cools, the theory proposes, these links begin to freeze into place, locking into a stable, orderly lattice. It's not unlike how water molecules, jostling wildly in liquid form, suddenly settle into the rigid symmetry of ice when temperatures drop. What's electrifying about this idea is how neatly it could explain some of cosmology's biggest puzzles. Take the horizon problem. Why does the cosmic microwave background, the afterglow of the Big Bang, look so uniform in all directions? If space-time started as a chaotic graph, its freezing transition could have transmitted information across vast distances almost instantly, smoothing out disparities before the graph settled into its current form. Even more intriguing, quantum gravity might offer a fresh take on dark energy. Those frozen links in the cosmic lattice could still retain traces of their original dynamism, like tension in a crystal pushing space apart in a way that looks to us like an accelerating universe. But the real magic of quantum gravity lies in its testable predictions. Unlike some quantum gravity theories that remain frustratingly abstract, this framework suggests we might find echoes of the primordial graph in the fabric of space today. Just as ice cracks under stress, the frozen geometry of space-time could have defects, tiny tears, or dislocations where the graph didn't freeze perfectly. These cosmic cracks might subtly alter how light travels across the universe or how particles behave at extreme energies. Some researchers even speculate that high-energy cosmic rays could carry fingerprints of these defects, offering a way to probe the theory through observation. Of course, skeptics point out hurdles. For one, the mathematics of how a random graph freezes into a smooth, four-dimensional space-time is fiendishly complex. And without direct evidence of these graph defects, the theory remains a compelling what if. But its boldness is undeniable. By treating space-time not as a given, but as something that emerges from deeper chaos, quantum gravity forces us to reconsider everything we thought we knew about the universe's architecture. It's a reminder that reality's most fundamental layer might not be geometry, but something wilder, messier, a cosmic game of connections waiting for the right moment to snap into place. And if that's true, the universe we see is just the calm after an ancient storm. What if the force that keeps planets in orbit and galaxies spinning isn't a fundamental interaction at all, but more like the pressure in a steam engine, a byproduct of something far deeper? That's the provocative heart of entropic gravity, a theory by physicist Eric Verlin that reframes gravity as an emergent phenomenon, rising from the chaotic churn of quantum information like heat from a bustling crowd. While we've explored this idea before, its implications run even wilder when you realize it might erase one of cosmology's biggest mysteries, dark matter. Imagine tossing out the need for invisible particles and replacing them with a cosmic accounting error. a miscalculation in how we've been tallying the universe's entropy all along. Here's how it rewrites the rules. In Verlaine's view, gravity isn't a force transmitted through space-time but a statistical effect, akin to how temperature emerges from countless molecular collisions. Picture a stretched rubber sheet with marbles rolling across it. Classical gravity says the sheet's curvature guides the marbles. Entropic gravity flips this. The marbles themselves are rearranging the sheet's microscopic degrees of freedom, creating the illusion of curvature. It's thermodynamics in disguise. When a star orbits a galaxy's center, it's not responding to some unseen dark matter halo. It's reacting to the entropy gradient, the way information is distributed in the space around it. The theory's boldest claim, dark matter might just be a mirage. Astronomers have long invoked invisible matter to explain why galaxies rotate faster than Newton's laws predict. But entropic gravity's equations suggest that at galactic scales, the emergent effects of quantum information mimic the gravitational pull we've been attributing to dark matter. It's like realizing the ghost haunting your house was just the wind rattling loose pipes, no spectre needed. Some simulations even show Verlaine's math matching galactic rotation curves without dark matter's help, a tantalizing hint that we've been overcomplicating the cosmos. Critics, though, aren't ready to dismantle the dark matter paradigm just yet. They argue entropic gravity struggles to explain phenomena like the bullet cluster, where colliding galaxies seem to separate visible matter from its gravitational effects, a hallmark of dark matter's existence. Others point out that Verlaine's framework leans heavily on holographic principles, which remain untested themselves. And then there's the elephant in the room. If gravity is emergent, why does it behave so precisely like a fundamental force in every experiment we've ever done? Yet the theory refuses to fade into obscurity. Recent work has extended entropic gravity to incorporate quantum entanglement, suggesting that the information bits driving emergent gravity might be entangled across vast distances, a twist that could bridge it with other quantum gravity approaches. Meanwhile, astronomers are scouring galaxy surveys for anomalies that might favor Verlaine's predictions over dark matters. Whether it's ultimately proven right or wrong, entropic gravity's real triumph is its audacity. It forces us to ask, what if we've been misreading the universe's ledger all along, mistaking a cosmic side effect for the main event? And in that question lies the thrill of science at its most daring, where the answers we take for granted might just be placeholders for truths far stranger. Imagine a world where every particle you know, electrons, quarks, photons, has a hidden twin, a mirror image with slightly different properties. This isn't the plot of a sci-fi novel. It's the essence of supersymmetry, one of the most elegant ideas in theoretical physics. The theory proposes that every fundamental particle in the universe has a superpartner, a companion that could hold the key to taming the wild equations of quantum gravity. If proven, supersymmetry wouldn't just be a curiosity, it'd be a cosmic bomb, smoothing out the jagged infinities that plague our attempts to merge quantum mechanics and general relativity. Here's how it works. In the quantum world, particles are divided into two broad categories: fermions, like electrons and quarks, which make up matter, and bosons, like photons and gluons, which carry forces. Supersymmetry bridges this divide by suggesting each fermion has a bosonic superpartner and each boson has a fermionic twin. An electron, for instance, might pair with a selectron, while a photon could have a photino. These superpartners aren't just carbon copies, they differ in spin, a fundamental quantum property. This subtle tweak isn't arbitrary, it's a mathematical lifeline. When these twins are factored into quantum gravity calculations, their interactions cancel out the pesky infinities that normally derail the math, like two waves crashing together and perfectly neutralizing each other. The implications ripple far beyond tidy equations. Supersymmetry could solve the hierarchy problem, one of physics' most nagging puzzles: why gravity is so absurdly weaker than the other forces. If superpartners exist, their contributions would naturally counterbalance the extreme masses predicted by quantum theory, leaving gravity's feebleness as an emergent property rather than a fluke. Even more tantalizing, the lightest superpartner could be the elusive dark matter, the invisible glue holding galaxies together. It's a theory that doesn't just patch holes, it weaves an entirely new tapestry. Yet for all its promise, supersymmetry faces a glaring problem. We haven't found a single superpartner. Particle colliders like the Large Hadron Collider have hunted for these twins at increasingly high energies, but so far the detectors remain stubbornly silent. Some versions of the theory predicted superpartners would appear at energies already probed, leading to whispers that supersymmetry might be in trouble. Critics argue it's a beautiful idea untethered from reality, a mathematical mirage that's failed to materialize, but supporters aren't ready to concede. They point out that superpartners could be heavier than expected, lurking just beyond our current reach. Others propose that supersymmetry might manifest in ways we haven't yet imagined, perhaps hidden in extra dimensions or disguised by exotic interactions. The theory's elegance keeps it alive, even as experiments tighten the noose around its simpler forms. Whether supersymmetry survives or crumples under scrutiny, its legacy is undeniable. It's shown us how deeply interconnected the universe's building blocks might be, and how profoundly symmetry could shape reality's deepest laws. And in that possibility, no matter how faint, lies the thrill of physics at its most daring, a chase for shadows that might rewrite everything we know. Think of a clock ticking each second, marking the relentless march of time. Now imagine that clock shattering, its pieces scattered into a void where before and after lose all meaning. That's the eerie world of the Wheeler-DeWitt equation, a mathematical beast that tries to cram Einstein's general relativity into the quantum realm, and in the process erases time itself from the universe's blueprint. Named after physicists John Wheeler and Bryce DeWitt, this equation isn't just difficult to solve, it's philosophically jarring, suggesting that the flow of time we experience might be nothing more than a cosmic illusion. At its core, the Wheeler-DeWitt equation is an attempt to quantize gravity by treating the entire universe as a quantum object. Unlike Schrödinger's equation, which describes how quantum systems evolve over time, the Wheeler-DeWitt equation stubbornly lacks any time variable at all. It's a snapshot frozen in mathematical amber, describing the universe in a single, eternal instant. Picture a movie where every frame is identical, no plot, no progression, just a static image claiming to encapsulate the entire story. This timelessness emerges because general relativity already treats time as malleable, bending and twisting alongside space. When you quantize that flexible fabric, time doesn't just bend, it vanishes. Reactions to this idea range from awe to exasperation. Supporters hail the equation as a revelation, a clue that time might be emergent, a side effect of deeper quantum processes like temperature arising from atomic motion. Carlo Rovelli, a leading voice in loop quantum gravity, argues that the Wheeler-DeWitt equation isn't broken. It's pointing us toward a reality where time isn't fundamental. But critics fire back. If the equation can't explain why we perceive time's flow, is it even physics? Even DeWitt himself reportedly recoiled from the equation's implications, calling its timelessness distasteful. The equation's mathematical spine is no less polarizing. It's a differential equation operating on the wave function of the universe, a concept so abstract it makes quantum particles look mundane. Solving it requires wrestling with the infamous problem of time, a paradox that's birthed countless interpretations. Some theorists propose that time re-emerges when you factor in quantum observers, like how a 3D hologram materializes from 2D data. Others suggest the equation's static solution contains every possible now, simultaneously, with our experience of time just a path we trace through this frozen landscape. Yet for all its controversy, the Wheeler-DeWitt equation refuses to be ignored. Cosmologists still lean on it when probing the universe's birth, as its timeless framework might hold clues about what preceded the Big Bang. Quantum gravity researchers dissect its structure for hints about how space-time could emerge from something deeper, and philosophers mine it for insights into the nature of existence itself. Whether it's a dead end or a roadmap, this enigmatic equation forces us to confront a humbling truth. The universe's deepest layers might not just defy our intuition, they could erase the very concept of when altogether. Picture a universe where the laws of physics near its boundary are a perfect mirror of everything happening inside a cosmic echo so precise. It rewrites how we think about space, time, and gravity itself. That's the radical promise of AD/CFT correspondence, a cornerstone of string theory so profound, it blurs the line between dimensions. At its heart, this idea proposes an astonishing trade. The chaotic, gravity-filled depths of a theoretical universe called anti-de Sitter space are mathematically equivalent to a quantum field theory painted on its outer shell. It's as if the entire volume of a soda can could be perfectly encoded in the label wrapped around it. Every bubble, every fizz, every swirling drop inside reduced to flat, two-dimensional data. Anti-de Sitter space, or AD/S for short, isn't like our universe. It's a warped, hyperbolic realm where gravity bends spacetime so sharply, light sent outward eventually curves back like a boomerang. But its strangeness is precisely what makes AD/S/CFT so powerful. The CFT stands for conformal field theory, a type of quantum theory that lives on the boundary of this twisted cosmos, immune to gravity's pull. The correspondence claims these two worlds, though seemingly unrelated, are indistinguishable in their physics, a black hole tunneling through AD/S's depths. That's just a seething quantum particle collision on the boundary, a star collapsing in the interior, a ripple in the boundary's quantum soup. To grasp why this isn't just mathematical sleight of hand, think of a hologram. Shine light on its flat surface and a three-dimensional image springs to life. The hologram isn't literally 3D, it's an illusion crafted from interference patterns on a 2D film. AD/S/CFT suggests reality might work the same way. Our seemingly three-dimensional universe, with its galaxies and gravity, could be a projection of quantum information scrawled on some distant, lower-dimensional surface. It's a notion that turns the holographic principle from metaphor into rigorous mathematics, offering a concrete bridge between quantum mechanics and Einstein's gravity. The implications are staggering. Black holes, those infamous information destroyers, become test cases. In AD/S/CFT, a black hole's interior is dual to a hot, chaotic quantum state on the boundary, one where information isn't lost, just scrambled like an egg. This could resolve the black hole information paradox, suggesting Hawking was right. Information escapes, just informs we're only beginning to decode. Even more tantalizing, the correspondence hints at a unifying language for physics. The equations of quantum field theory, traditionally divorced from gravity, suddenly become tools to explore it, like using a sonogram to map a hidden organ. Yet AD/S/CFT isn't a perfect mirror of our universe. Anti-de Sitter space's negative curvature makes it a mathematical playground, not a twin of our flat, expanding cosmos. Critics argue it's a beautiful answer to a question nature might not be asking, but its defenders counter that even idealized models can reveal universal truths, just as studying perfect crystals helps us understand messy real-world materials. And in labs today, researchers are simulating AD/S/CFT in tabletop quantum systems, watching as abstract duality springs to life in chilled atoms and lasers. Whether AD/S/CFT is the final word or just a stepping stone, its real gift is perspective. It forces us to ask, what if dimensions are optional? What if gravity's tyranny is just a shadow of something simpler, playing out on the edges of reality? In a universe that thrives on connections, this correspondence reminds us that the deepest links might be the ones we're only beginning to trace between the vast and the vanishingly small, the curved and the flat, the inside and the out. Spin foam models take the loop quantum gravity framework and inject it with raw dynamism picture space-time, not as a static tapestry of woven loops, but as a frothing, ever-shifting quantum sea where every ripple is a decision, a transition between possible geometries. If loop quantum gravity gives us the threads of reality, spin foams show us how those threads knot, unknot, and reweave themselves moment by moment. At their core, these models represent space-time as a network of spinning, interlocking surfaces called foam, where each bubble or cell carries quantum information about its shape and connection to neighboring cells. It's like watching a cosmic kaleidoscope where every twist rearranges the patterns of space itself. What makes spin foams electrifying is how they handle change. In general relativity, space-time bends smoothly like a rubber sheet, but in the quantum realm, change happens in jumps, discrete, quantized leaps. Spin foams capture this by treating every transition between space-time states as a kind of quantum event, where the foam's structure updates itself in finite steps. Imagine flipping through a flipbook where each page isn't just a slight variation of the last, but a complete reshuffling of the cosmic deck. This granularity isn't arbitrary. It's a direct consequence of quantizing gravity, ensuring that even the wildest fluctuations stay finite and calculable. Nowhere is this more radical than in black hole physics. Traditional models break down at singularities, where densities and curvatures spiral toward infinity. But spin foams offer a way out. Simulations using these models suggest that inside a black hole, space-time doesn't crumple into a meaningless point. Instead, the foam's quantum cells reach a maximum density and then rebound. The collapse reverses like a compressed spring recoiling. Some theorists argue this could mean black holes aren't eternal graves for information, but temporary knots in the quantum fabric, eventually unraveling into new space-time structures. It's a vision that sidesteps the need for firewalls or Hawking radiation alone to resolve the information paradox, proposing instead that black holes might transform rather than destroy. Yet spin foams aren't just about cosmic extremes, they're also a toolkit for probing the universe's everyday quantum texture. By simulating how foam cells interact, physicists can explore questions like, does space-time have a fundamental graininess at the Planck scale? Could quantum fluctuations in the foam leave imprints on light traveling across the universe? Some even speculate that if we could peer deeply enough into the fabric of reality, we'd see a shimmering, probabilistic foam where every possible geometry flickers in and out of existence, with our classical universe as the statistically dominant pattern. Challenges, of course, remain. Spin foam models are notoriously complex, their equations bristling with variables that push supercomputers to their limits. And without experimental evidence, no telescope or particle collider can yet probe the Planck scale. These ideas linger in the realm of mathematical beauty. But their promise is undeniable. If spin foams are right, the smooth, deterministic space-time of Einstein's era might be an illusion, a cosmic average of something far wilder beneath. And in that turbulence, we might finally find the missing link between the quantum and the cosmic. What if the key to solving quantum gravity's endless headaches lies in breaking one of physics' most sacred symmetries? That's the provocative gamble of Horava-Lifshitz gravity, a theory that dares to treat time and space as fundamentally unequal at the universe's most extreme scales. Named after physicist Petr Horava and inspired by earlier work by Evgeny Lifshitz, this framework rips up Einstein's playbook where space and time blend seamlessly into a four-dimensional continuum. Instead, it proposes that at ultra-high energies like those in the early universe or near black hole singularities, time becomes a privileged dimension, governed by different rules than the three spatial ones we know. It's as if the cosmos, under enough pressure, snaps into a kind of quantum dictatorship where clocks tick to a rhythm that rulers and compasses can't follow. The theory's radical power emerges from this asymmetry. By allowing time to decouple from space at microscopic scales, Horova-Lifshitz gravity sidesteps the mathematical nightmares that plague other quantum gravity approaches. Normally, attempts to quantize Einstein's equations generate infinite terms, nonsensical results where probabilities balloon beyond 100% or curvatures spiral into unreality. But here, time's unique behavior acts like a regulatory filter, suppressing those infinities before they can derail the math. Picture a chaotic classroom where one student time suddenly stands up and imposes order, silencing the cacophony of diverging equations. The result, a theory where gravity becomes renormalizable, meaning its quantum calculations stay finite and meaningful, just like the other fundamental forces. But the real magic happens in cosmology. Horova-Lifshitz gravity's temporal rigidity could explain why the early universe didn't tear itself apart. In standard Big Bang models, the insane energies of the first moments should have generated wild quantum fluctuations in space-time itself. Yet somehow, the cosmos emerged with startling smoothness. This theory suggests that time's privileged role acted like a cosmic damper, suppressing those fluctuations and allowing structure to coalesce. Even more intriguing, it might eliminate the need for cosmic inflation, the controversial idea that the universe underwent a brief, hyper-accelerated expansion shortly after the Big Bang. Instead, Horova-Lifshitz gravity's built-in asymmetry could naturally produce the large-scale uniformity we observe, no additional mechanisms required. Critics, though, aren't ready to abandon Einstein's symmetry just yet. They point out that violating Lorentz invariance, the principle that physics works the same for all observers regardless of motion, is a steep price to pay. Experiments have hunted for Lorentz violations for decades, from particle colliders to studies of distant gamma-ray bursts, and so far, space-time's symmetry has held firm. Yet Horova-Lifshitz proponents counter that these tests probe relatively low energies. At the Planck scale, where quantum gravity reigns, all bets might be off. Some versions of the theory even predict subtle Lorentz violations that future ultra-precise atomic clocks or gravity wave detectors could catch, offering a potential smoking gun. The debate reflects a deeper tension in physics. Do we preserve cherished symmetries at all costs or sacrifice them for progress? Horova-Lifshitz gravity's audacity lies in choosing the latter, gambling that the universe's deepest laws might not be as elegant as we'd hoped, but more solvable. Whether it's a temporary fix or a glimpse of reality's true face, the theory reminds us that sometimes breaking rules isn't rebellion. It's the only way to move forward. Einstein's general relativity gave us a universe where gravity is the curvature of space-time, a smooth, geometric dance where matter tells space how to bend, and space tells matter how to move. But what if that dance has a hidden twist, literally? Quantum Einstein-Cartan theory takes Einstein's masterpiece and scribbles in the margins, adding a radical new feature: torsion, the idea that space-time doesn't just curve, it can also twist like a corkscrew. This subtle tweak doesn't just reimagine gravity, it could erase the universe's most terrifying singularities and rewrite the story of cosmic inflation, all while giving fermions, the particles that make up matter, a starring role in shaping the cosmos. Torsion isn't a new idea. Mathematicians like Eli Cartan explored it a century ago, but it was overshadowed by Einstein's curvature-centric approach. In the quantum Einstein-Cartan framework, torsion emerges from the intrinsic spin of particles, particularly fermions like electrons and quarks. Picture space-time not as a static trampoline sagging under mass, but as a dynamic fabric that twists wherever particles with spin are present. Every electron, every quark becomes a tiny spindle, imparting microscopic twists to the space around it. These twists don't just vanish, they accumulate, weaving torsion into gravity's equations in a way that changes everything. The most dramatic payoff, black hole singularities might vanish. In general relativity, a collapsing star's gravity warps space-time into an infinitely dense point, a mathematical absurdity where physics breaks down. But torsion acts like a cosmic safety net. As matter collapses, the spin of its particles generates torsion fields that grow stronger, eventually resisting further collapse. Instead of a singularity, you get a bounce, a moment where collapse reverses like a spring recoiling. It's an elegant fix that mirrors loop quantum gravity's predictions but comes from an entirely different direction, hinting at a deeper truth. Singularities might be relics of an incomplete theory, not reality. But the surprises don't stop there. Torsion could also hold the key to cosmic inflation, the universe's explosive early growth spurt. In standard models, inflation is driven by a mysterious, inflaton field, but quantum Einstein-Cartan theory offers an alternative. Fermions, ubiquitous in the early universe, could have generated colossal torsion fields that acted as a repulsive force, flinging space apart at unimaginable speeds. It's a tantalizing thought. The same twist that prevents singularities might also explain why the cosmos is so vast and smooth, yet the theory isn't without skeptics. Detecting torsion's subtle effects is daunting. It would require measuring space-time's twist on scales far smaller than any experiment has probed, and some argue that torsion's influence diminishes so rapidly with distance that it's negligible on cosmic scales. But proponents counter with a thrilling possibility. If torsion exists, it might leave fingerprints in the polarization of the cosmic microwave background or the behavior of spinning neutron stars. Even if it's invisible, its gravitational echoes could linger. What makes quantum Einstein-Cartan theory so compelling isn't just its solutions, it's the way it rebalances gravity's ledger. For decades, we've treated matter as a passive passenger on space-time's curves. Here, matter actively reshapes geometry through spin, turning every particle into a cosmic sculptor. It's a reminder that the universe's deepest truths might not lie in tearing down Einstein's work, but in uncovering the hidden layers he might have missed one twist at a time. What if our universe isn't floating alone in the void, but is just one slice of something far larger, a cosmic loaf of bread where each slice is its own universe, drifting in a hidden dimension we can't see? That's the mind-bending premise of Brane Cosmology, a theory that reimagines the Big Bang not as a singular explosion, but as the aftermath of a colossal collision between our universe called a brane and another lurking in the shadows of higher dimensional space. Picture two sheets of paper suspended parallel to each other in a dark room. If they suddenly smacked together, the energy of that impact could birth everything we know: stars, galaxies, even time itself. And if string theory is right, this might not have happened just once, but over and over in an endless cycle of cosmic collisions. The word brane comes from membrane, but don't think flimsy plastic wrap. In this context, branes are dynamic, multidimensional surfaces where entire universes could be pinned like posters on a wall. String theory suggests these branes exist in a higher dimensional bulk, a realm beyond our four-dimensional reach. Our entire cosmos, with its galaxies and black holes, might be confined to just one of these branes, like ants crawling across a leaf, oblivious to the forest beyond. But sometimes those branes move. When they do, their collisions could unleash enough energy to ignite new universes, each with its own laws, its own physics, even its own version of time. This idea turns the Big Bang into something far stranger, not a beginning from nothing, but a reboot from something. The leading model, called the ekpyrotic universe scenario from the Greek word for conflagration, proposes that our universe was born when two branes, each possibly hosting its own pre-existing universe, smashed together in the bulk. The violence of that crash would have been unimaginable, heating the brain to trillions of degrees and flooding it with the raw material of reality. But here's the twist: because branes can oscillate, drifting apart and crashing back together, this process might repeat eternally. No singular creation, just an endless loop of collisions, expansions, and contractions, a multiverse with its own heartbeat. The echoes of these collisions might still be visible today. Some theorists argue that the cosmic microwave background, the afterglow of the Big Bang, could bear faint scars from a brane collision, subtle temperature variations that our telescopes haven't yet spotted. Others suggest that gravitational waves, ripples in space-time from the universe's violent infancy, might carry signatures of these higher dimensional crashes. If we could decode those signals, we might glimpse the hidden architecture of the bulk itself, proof that we're not alone in the cosmic loft. But Brane Cosmology's wildest implication isn't just about our past, it's about our neighbors. If branes float freely in the bulk, then other universes could be hovering just millimeters away in a dimension we can't perceive. Gravity, unlike other forces, might leak between branes, which could explain why it's so weak compared to electromagnetism or the nuclear forces. And if two branes brush too close, the gravitational tug-of-war could warp galaxies, fling stars, or worse, rip a universe apart. It's a chilling thought. The apocalypse might not come from within our cosmos, but from a chance encounter with another, unseen one. String theory purists love Brane Cosmology for how neatly it ties into their larger framework. If strings are the universe's fundamental ingredients, branes could be the plates they're served on, higher dimensional anchors that give strings a stage to vibrate upon. Critics, though, argue it's all untestable poetry. Without direct evidence of extra dimensions or brane collisions, the theory remains a dazzling what-if. But in a field where imagination is the sharpest tool, Brane Cosmology dares us to rethink the simplest questions. Where did we come from? And more thrillingly, what else is out there just beyond the edge of our brain? Einstein's theory of relativity is the foundation of modern physics, a masterpiece that reshaped our understanding of space and time. But what if it's incomplete? Doubly special relativity dares to tweak Einstein's equations by introducing a cosmic speed limit and a minimum length, the Planck scale, where space-time itself might pixelate into the smallest possible units. It's like rewriting the rules of a game to account for the fact that the board isn't infinitely smooth but has a hidden grid beneath. This tiny adjustment ripples outward, warping how energy, momentum, and even light behave at the universe's most extreme scales. At the heart of this theory lies a radical idea. The Planck length isn't just a curiosity, it's a fundamental boundary, a line the universe won't let us cross. In ordinary relativity, a high-energy photon's wavelength could shrink indefinitely as its energy grows. But doubly special relativity imposes a flaw. No matter how much energy you pump into that photon, its wavelength can't squeeze smaller than the Planck length. This tweak doesn't just tweak the math, it rewires reality's wiring. Suddenly, particles with mind-bending energies don't behave as expected. Their momentum, their interactions, even the way they experience time start to deviate from Einstein's predictions in subtle, measurable ways. One of the most tantalizing consequences involves gamma-ray bursts, the universe's most violent explosions. These cosmic fireballs fling high-energy photons across billions of light-years, and according to doubly special relativity, those photons shouldn't all arrive at the same time. If space-time has a graininess at the Planck scale, higher energy photons would interact with it slightly differently than their lower energy counterparts, creating a tiny delay in their travel times. It's as if the universe is a bumpy road and the fastest cars hit more potholes. Astronomers have hunted for this delay in gamma-ray burst data, hoping to catch space-time's pixelation in action. The results aren't definitive yet, but each new burst offers another chance to catch the universe red-handed, revealing its hidden quantum structure. But the theory's implications run deeper than astrophysical detective work. By blending relativity with a minimum length, doubly special relativity bridges the gap between Einstein's smooth space-time and the chaotic quantum world. It suggests that at energies approaching the Planck scale, the very concept of distance becomes fuzzy, like a photograph stretched too thin. Two observers might not even agree on how far apart objects are because their measurements bump up against the universe's fundamental grain. This isn't just measurement error. It's a hint that space-time itself might be a statistical illusion emerging from something far stranger beneath. Critics argue that the theory's deviations from standard relativity are too subtle to test conclusively, lost in the noise of cosmic distances and instrumental limits. Others question whether imposing a minimum length truly solves quantum gravity's deeper puzzles or just papers over them. But supporters counter with a compelling thought. If doubly special relativity is right, we're not just tweaking Einstein's equations, we're glimpsing the edge of reality's rulebook where the old laws fray and new ones take hold. And in that fraying, we might finally find the threads that weave quantum gravity into being. What if we've been focusing on the wrong aspect of space-time all along? Shape dynamics flips the script on Einstein's geometric universe, proposing that what truly matters isn't the curvature of space-time, but its shape, the relational patterns between objects that persist even when the underlying geometry shifts. Imagine a sculpture molded from clay. You could stretch or twist it, changing its geometric properties, but its essential form, the way its parts connect, might remain intact. Shape dynamics argues that this relational structure, not the metric fabric of general relativity, is the bedrock of reality, and this subtle shift could be the key to taming quantum gravity's mathematical chaos. At its core, shape dynamics trades Einstein's metric tensor, the mathematical object that encodes how space-time curves, for a leaner, more flexible framework built on conformal geometry. Here, angles and ratios take precedence over absolute distances. Picture a cosmic game of connect the dots where only the relative positions of stars, galaxies, and particles matter, while the space between them becomes secondary. This isn't just philosophical hand-waving. It's a concrete mathematical reformulation where gravity emerges from the universe's relentless drive to optimize these relational configurations. The equations simplify dramatically because they no longer need to account for redundant geometric degrees of freedom, like trimming the fat from an overcomplicated recipe. The payoff, a potential bridge between relativity and quantum mechanics. In standard approaches, quantizing gravity forces physicists to grapple with diffeomorphism invariance, a technical hurdle meaning the equations must hold true no matter how you stretch or twist the coordinates of space-time. Shape dynamics sidesteps this by focusing on invariant shapes, which are inherently more compatible with quantum theory's discrete relational nature. It's like switching from trying to quantum mechanically describe every ripple in a pond to instead tracking only the interference patterns those ripples create, a far cleaner starting point for quantization. Critics initially dismissed shape dynamics as a clever repackaging of existing ideas, but its proponents point to startling successes. For instance, in black hole physics, the theory naturally avoids singularities by replacing them with shape singularities, points where relational structure breaks down but without infinite densities. Similarly, cosmological models built on shape dynamics can reproduce the large-scale structure of the universe without invoking dark energy as a separate ingredient. The cosmic acceleration might just be an emergent effect of the universe optimizing its global shape over time. Yet challenges linger. The theory struggles to fully incorporate matter fields, and some argue its relational framework is too minimalist, stripping away geometric tools that remain empirically useful. But in a field where progress often hinges on radical simplification, shape dynamics offers a provocative reminder. Sometimes the deepest truths aren't found in the equations we've mastered, but in the ones we've yet to imagine. And if shape is indeed fundamental, then reality might be less like a flexible fabric and more like an eternal dance, where the steps matter infinitely more than the stage. Imagine every particle, every ripple of space-time as a tiny scrap of data, not just passive information, but active, dynamic bits that collectively weave the fabric of reality itself. Quantum information theory proposes exactly this, that space-time isn't a static stage, but a roaring ocean of quantum bits, qubits entangling and disentangling in a cosmic dance. At its core, this idea suggests gravity itself might emerge from the way these qubits link together, like the threads of a vast, invisible tapestry determining how tightly or loosely the universe hangs together. The theory's radical power comes from its ability to bridge two seemingly unrelated worlds, quantum entanglement and black hole physics. Entanglement, that eerie connection where particles instantly influence each other across vast distances, might be the glue holding space-time together. Picture two qubits entangled deep inside a black hole. Their connection isn't just a quantum curiosity, it could be the gravitational pull we observe, a force born from information's insistence on staying correlated. The more entangled qubits are, the stronger the space-time fabric between them, like stitches pulled taut. This is more than metaphor. Calculations show that in certain models, Einstein's equations of general relativity emerge naturally from entanglement's web. Nowhere is this more dramatic than at black hole event horizons. In 2012, physicists Ahmed Olmary, Donald Maroff, Joe Pulczynski, and James Sully, collectively dubbed the AMPS team, dropped a bombshell. If entanglement builds space-time, then the smooth horizon predicted by Einstein might be an illusion. Instead, an infalling astronaut wouldn't glide effortlessly into the black hole. They'd smash into a seething wall of high-energy particles, a firewall cooked up by quantum contradictions. Here's why. If entanglement connects the inside and outside of a black hole, and quantum mechanics forbids copying or destroying information, then the horizon must either violently disrupt or preserve these links. Either way, the tranquil vacuum of relativity gives way to quantum fury. The implications ripple outward. If space-time is built from qubits, then black holes aren't just cosmic trash compactors. They're the ultimate quantum computers, their interiors a froth of entangled information processing. The it from bit philosophy championed by physicist John Wheeler takes on new life. Maybe the universe isn't just described by information, maybe it is information. Every galaxy, every photon, every law of physics could be a pattern in this quantum code, with gravity as the algorithm governing how those patterns interact. Skeptics, though, raise valid concerns. If entanglement is so fundamental, why don't we see its effects in everyday gravity? Why does Earth's orbit obey Newton's old equations, not some quantum informational rule? Supporters counter that at macroscopic scales, the noisy, statistical nature of entanglement averages out to classical behavior, like how the jittering of atoms smooths into the solidity of a table. Others worry that quantum information theory, while elegant, lacks experimental hooks. How do you test whether space-time is made of qubits when those qubits are buried beneath layers of abstraction? Yet the theory's boldness keeps it alive. Recent experiments with quantum computers simulate toy models of holographic space-time, watching as entanglement generates geometry-like structures. Telescopes scour the sky for anomalies in black hole mergers, hunting for echoes of firewalls or other quantum gravitational signatures. And theorists keep refining the math, probing whether all of reality might one day be derived from a single, staggering principle, that to exist is to be entangled, to be stitched into the universe's vast, vibrating quantum tapestry. Whether it's the final answer or just another clue, quantum information theory reminds us that the universe's deepest layer might not be stuff or energy, but the relentless, invisible hum of information connecting everything. Imagine looking at the night sky and realizing everything you see, every star, every galaxy, is just one tiny patch of a reality so vast it defies comprehension. Causal patch cosmology embraces this staggering limitation, suggesting that when we talk about quantum gravity and the universe's origins, we shouldn't waste energy theorizing about regions forever beyond our cosmic horizon. Instead, we should focus solely on what's causally connected to us, the observable patch where light has had time to reach us since the Big Bang. It's a humbling perspective. The universe might be infinite, but physics only truly matters within the finite sphere we can touch, measure, and test. This shift in focus isn't just philosophical pragmatism. It's a survival tactic against some of cosmology's weirdest paradoxes. Take the multiverse. Many theories, from eternal inflation to string theory's landscape, predict a fractal foam of infinite universes bubbling into existence beyond our view. But infinity is a double-edged sword. It implies that every possible event, no matter how absurd, must happen somewhere. Enter Boltzmann brains, self-aware entities that randomly fluctuate into existence from quantum chaos, complete with false memories of living in an ordered universe. If the multiverse is truly infinite, these disembodied observers should statistically outnumber real beings like us by unimaginable margins. So why don't we wake up as Boltzmann brains hallucinating reality? Causal patch cosmology offers a ruthless solution. If we ignore unobservable regions, the paradox vanishes. Our patch has a finite history, roughly 13.8 billion years, making the odds of a Boltzmann brain spontaneously forming in our causal vicinity astronomically low. The theory doesn't deny the multiverse's existence. It simply declares those other universes irrelevant to our physics. Like sailors navigating by the stars they can see, we build our theories only from the light that reaches us. But the implications run deeper than dodging Boltzmann nightmares. By treating our causal patch as the arena for quantum gravity, physicists can sidestep the mathematical quicks and of trying to describe an entire multiverse. The Big Bang singularity, for instance, becomes less a universal beginning and more a local event. One of countless nucleation points in a larger cosmic foam, but the only one we'll ever need to explain. This approach also reshapes dark energy's mystery. If space's accelerating expansion eventually isolates our patch entirely, severing all future causal links to distant galaxies, does it even make sense to ponder their ultimate fate? Critics argue this view is myopic, that physics should aspire to describe reality's totality, not just our corner of it. Others counter that science, by definition, is the study of the observable. After all, if a tree falls in a universe forever cut off from ours, does it make a sound we'll ever need to explain? Causal patch cosmology doesn't claim to have all the answers, but its razor-sharp focus on the knowable might just be the compass we need to navigate quantum gravity's stormiest seas. In a cosmos teeming with unknowns, sometimes the most radical act is admitting what we can and can't ever see. Before supercomputers could simulate the frothing quantum foam of modern theories, physicists needed a simpler way to approximate the warps and weaves of space-time. A mathematical stepping stone between Einstein's smooth continuum and the pixelated reality lurking beneath. Enter Reg calculus, a clever trick from the early days of quantum gravity that sliced space-time into a mosaic of triangular blocks like a cosmic geodesic dome. Named after Italian physicist Tullio Reg, this approach didn't try to quantize gravity head-on. Instead, it treated general relativity as a puzzle to be assembled from discrete, flat pieces, each bending reality only at their edges where they snapped together. Picture building a curved sculpture out of stiff cardboard polygons. The more triangles you use, the smoother the surface appears, but underneath, it's all sharp angles and straight lines. What made Reg calculus revolutionary was its computational elegance. By modeling space-time as a network of interconnected triangular hinges, physicists could simulate complex gravitational phenomena, like the collapse of a star or the orbit of a planet, without drowning in the infinite complexities of continuous curvature. Each hinge carried a deficit angle, a measure of how much the triangles failed to lie flat when joined, and these deficits encoded the gravitational field's strength. It was relativity rendered in Lego. Black holes became clusters of tightly packed triangles, gravitational waves rippled as synchronized hinge adjustments, and the Big Bang transformed into a primal tessellation straining at its seams. Yet for all its ingenuity, reg calculus was always a placeholder, a bridge to deeper truths. Modern approaches like causal dynamical triangulations or spin foams have inherited its discrete spirit but injected quantum weirdness into the mix. Where Reg's triangles obeyed classical rules, today's simulations let those shapes fluctuate probabilistically, merge, or even vanish entirely. The difference is like comparing a stop-motion animation to a living, breathing organism. Still, Reg's legacy persists in unexpected places. Computer graphics algorithms use his methods to render curved surfaces in video games, and some quantum gravity researchers still employ his calculus as a sanity check, a classical yardstick against which to measure their wilder quantum predictions. The lesson here isn't just about triangles, it's about how progress in physics often walks a winding path, where even obsolete tools can carve footholds for the next climb. Reg's humble lattice couldn't capture the quantum churn beneath space-time, but it proved something profound. Sometimes, to grasp the universe's infinite complexity, you need to start with the simplest possible pieces and let the cosmos assemble itself from there. Einstein taught us that nothing travels faster than light, a cosmic speed limit etched into the fabric of relativity. But what if gravity, the architect of space-time itself, doesn't always play by those rules? Non-local gravity dares to propose exactly that, suggesting that at the universe's most fundamental scales, gravitational effects can leap across vast distances instantaneously, untethered by the sluggish speed of light. This isn't just a tweak to the rules, it's a wholesale reimagining of how cause and effect might operate in the quantum realm, with profound consequences for everything from black holes to the accelerating expansion of the cosmos. At the heart of this idea is a radical challenge to locality, the principle that objects interact only with their immediate surroundings. Think of it like a game of telephone where each particle passes messages only to its nearest neighbors. Non-local gravity, by contrast, imagines particles whispering directly to one another across the void, as if the phone lines were pre-installed at the birth of the universe. This isn't pure speculation mathematically. It emerges from theories trying to reconcile quantum entanglement's spooky action at a distance with gravity's relentless grip. If entangled particles can influence each other instantly, why shouldn't gravity, the force that literally shapes reality, have its own quantum backchannels? One of the most tantalizing implications involves dark energy, the mysterious force accelerating the universe's expansion. Traditional models treat dark energy as a static property of space itself, but non-local gravity offers a wild alternative. What if it's not a thing at all, but an emergent effect of gravitational interactions smearing across space-time? Picture tossing a pebble into a pond and watching the ripples spread. Now imagine those ripples don't fade, they pile up over billions of years, their cumulative energy pushing galaxies apart. Non-local gravity's equations suggest something similar could happen on cosmic scales, with gravitational influences from the early universe still echoing today, driving expansion without any need for dark energy's elusive particles. The real test, of course, is whether we can catch this non-local sleight of hand in action. Experiments are already hunting for anomalies in gravitational waves, subtle delays or correlations that might betray gravity's quantum shortcuts. Other proposals involve ultra-precise atomic clocks placed in orbit, monitoring whether the pull of Earth's gravity fluctuates faster than light speed should allow. Even the cosmic microwave background might hold clues, its faint imprints potentially encoding signs of primordial non-locality, but skeptics aren't convinced. Violating locality risks reopening Pandora's box of paradoxes, like time-traveling signals that could scramble causality itself. And without a clear mechanism for how non-local gravity knows where to act across space-time, the theory walks a fine line between groundbreaking and ad hoc. Yet its defenders counter, maybe the universe doesn't owe us intuitive mechanisms. After all, entanglement once seemed impossible too, until it became the backbone of quantum computing. Whether non-local gravity survives scrutiny or not, its boldness forces us to confront a humbling truth. The cosmos might not just be stranger than we imagine, but stranger than we can imagine. And in that strangeness, we might finally find the keys to quantum gravity's deepest mysteries. Einstein's general relativity painted gravity as the curvature of space-time, a cosmic trampoline sagging under the weight of planets and stars. But what if we've been staring at the wrong geometric feature this whole time? Teleparallel gravity flips the script, proposing that gravity isn't about bending at all, it's about twisting. Instead of matter warping the fabric of space-time into hills and valleys, this theory suggests gravity emerges from torsion, a subtle spiraling of the cosmic loom that's been hiding in plain sight. Picture a DNA helix compared to a crumpled sheet of paper. Both describe shapes, but one twists while the other folds. Teleparallel gravity argues the universe prefers the twist. The math behind this is deceptively elegant. While general relativity relies on the curvature of connections between space-time, points the so-called Levi-Civita connection, teleparallel gravity swaps it for the Weizenberg connection, a geometric tool that tracks how space-time rotates locally as you move through it. On the surface, the equations still predict planets orbiting stars and light bending around galaxies, just like Einstein's theory, but dig deeper and the differences become profound. For starters, teleparallel gravity naturally sidesteps the black hole singularities that plague classical relativity. Where general relativity predicts infinite densities at a black hole's core, torsion introduces a repulsive effect at extreme scales, like a cosmic spring that resists being wound too tightly. The result, collapsing matter rebounds instead of crushing into oblivion, a cosmic bounce that could rewrite the fate of dying stars. This twist-centric view also offers a fresh path toward unifying gravity with quantum mechanics. In teleparallel gravity, the gravitational field resembles the gauge fields of particle physics, the same mathematical structures governing electromagnetism and the nuclear forces. That similarity isn't accidental. It hints at a hidden symmetry where gravity might just be another thread in the quantum tapestry, not an outsider demanding special treatment. Some versions of the theory even incorporate torsion into the standard model, suggesting that the same mechanism causing electrons to spin could also shape the geometry of the cosmos. It's a tantalizing hint that the universe's largest and smallest scales might finally share a common language, but the theory isn't without skeptics. Critics argue that teleparallel gravity's predictions are often indistinguishable from general relativity in most observable scenarios, like two chefs using different recipes to bake identical cakes. Without a smoking gun experiment to prove torsion's role, the debate risks becoming philosophical. Yet supporters point to subtle divergences in extreme environments, the spin of neutron stars, the afterglow of black hole mergers, or the universe's expansion rate. If torsion exists, its fingerprints might hide in the way gravitational waves ripple or how dark energy accelerates the cosmos. Even more intriguing, teleparallel gravity could eliminate the need for dark matter altogether, with torsion's geometric effects mimicking the extra gravitational pull we've been attributing to invisible particles. Whether it's a true paradigm shift or just a clever reformulation, teleparallel gravity's real gift is perspective. It reminds us that sometimes the most profound breakthroughs come not from adding complexity, but from seeing the same puzzle from a new angle. After all, if gravity can twist space-time instead of bending it, What other cosmic truths might we be missing simply because we haven't thought to look sideways? Graphene, a single layer of carbon atoms arranged in a honeycomb lattice, might seem unrelated to black holes and the fabric of space-time. Yet this wonder material, studied in labs worldwide, is quietly staging a revolution in quantum gravity research. When electrons zip through graphene at relativistic speeds, they don't just behave like particles. They mimic cosmic phenomena, warping and curving their environment as if they're navigating a miniature universe governed by Einstein's equations. It's emergent gravity in a petri dish, a tantalizing hint that the universe's deepest secrets might be hiding in plain sight, etched onto a flake of pencil lead. This bizarre connection hinges on graphene's unique electronic structure. Under the right conditions, electrons in graphene move as if they're massless, their energy and momentum locked in a linear relationship that mirrors the behavior of particles near light speed. But here's the twist: impurities or deformations in the lattice can warp this electron behavior, creating effective, curved space-time for the electrons. Picture a marble rolling across a warped table. The paths it takes aren't straight, but curved by the table's distortions. In graphene, those curves obey equations strikingly similar to general relativity, with strain fields playing the role of gravitational forces. Suddenly, tabletop experiments can simulate black hole horizons or cosmic expansion, all without leaving the lab. One of the most jaw-dropping demonstrations involves pseudo-magnetic fields. By stretching graphene in precise patterns, researchers have engineered landscapes where electrons behave as if they're under the influence of intense gravitational fields, even though no actual gravity is at work. These experiments have reproduced analogues of quantum Hall effects, event horizons, and even Hawking radiation, the elusive glow predicted to escape black holes. In 2021, a team at MIT observed electron behavior near a graphene wormhole, where strain mimicked the warping of space-time around a cosmic tunnel. While no actual wormholes were traversed, the math governing the electron's motion was eerily identical to theoretical models of these hypothetical shortcuts through the universe. The implications ripple far beyond cool lab tricks. If gravity-like phenomena can emerge from humble materials, maybe real gravity itself is an emergent property, a side effect of deeper, more fundamental interactions we've yet to uncover. Condensed matter physicists now whisper about it from bit in a new context. Perhaps space-time isn't a primary ingredient of reality, but a collective hallucination of quantum particles interacting en masse, like the ripple of a flag emerging from countless threads fluttering in sync. Critics caution that these analogies have limits. Graphene's gravity is a mathematical mirage, not a true warping of space-time, yet the parallels are too precise to dismiss. Some theorists are even borrowing tools from condensed matter to tackle quantum gravity's thorniest puzzles, like how information escapes evaporating black holes. The dialogue between these fields is birthing hybrid ideas, like quantum graphity, where space-time emerges from a network of entangled quantum bits, much like graphene's conductivity arises from its atomic lattice. Whether graphene holds the key to quantum gravity or simply lights a detour, its lesson is profound. Sometimes, to grasp the cosmos, we don't need bigger telescopes or more powerful colliders. We just need to look closer at the materials under our fingertips, where the universe's grandest dramas play out in atomic whispers. Black holes have long been the ultimate cosmic paradox, regions where gravity becomes so intense that not even light escapes, and where the known laws of physics seem to break down completely. But what if the terrifying singularity at their core, that point of infinite density, doesn't exist at all? Enter fuzzball theory, a radical idea from string theory that swaps the nightmarish singularity for something far stranger. A tangled, vibrating sphere of strings, a fuzzball so complex that its surface seethes with quantum chaos. At the heart of fuzzball theory is a simple but profound shift in perspective. Instead of a black hole's interior collapsing into a featureless singularity, The theory proposes that the entire volume inside the event horizon is packed with strings, the same fundamental threads string theory claims make up all particles and forces. These strings don't just sit there, they twist, loop, and vibrate in an impossibly intricate dance, filling the black hole with a fuzzy, dynamic structure. It's as if the black hole's core isn't a void but a dense ball of quantum yarn, frayed and knotted beyond recognition. This might sound like a cosmetic change, but the implications are staggering. For starters, fuzzballs could solve the infamous black hole information paradox, the puzzle of what happens to the information locked inside a black hole when it evaporates via Hawking radiation. In the traditional view, information seemed lost forever, violating quantum mechanics' sacred rule that information can never be destroyed. But fuzzballs offer an elegant escape. Because their stringy surfaces store quantum information in their complex vibrations, nothing ever truly disappears into a singularity. When a fuzzball emits Hawking radiation, that radiation carries subtle imprints of the original information, like a smoky whisper of the star that collapsed long ago. The theory even caught the attention of Stephen Hawking himself. After decades of insisting black holes destroy information, he famously reversed his position in 2004, conceding that information might escape after all. While he didn't endorse fuzzballs explicitly, the theory's ability to preserve information aligns with his revised stance. It's a rare moment where string theory, often criticized for untestable abstraction, offers a concrete solution to one of physics' most vexing problems. Yet fuzzballs aren't without their critics. Detractors argue that the theory's reliance on string theory's unproven framework leaves it on shaky ground. Without experimental evidence for strings, let alone their ability to form fuzzballs, the idea remains a compelling what if. Others question how fuzzballs would form in the first place. If a collapsing star transitions into a fuzzball, what triggers strings to tangle in just the right way? And could fuzzballs ever be distinguished from classical black holes through observation? Despite these challenges, the theory's elegance keeps it in the conversation. Recent work suggests fuzzballs might leave subtle fingerprints in gravitational wave signals or the shadowy outlines of black holes glimpsed by telescopes like the Event Horizon Telescope. Even if fuzzballs aren't the final answer, they've already reshaped the debate, proving that sometimes the most monstrous paradoxes just need a little fuzz to unravel. When you think of unification in physics, grand equations or complex symmetries might come to mind, but few theories push the envelope of creativity quite like Garrett Lissie's E8 model or Stephen Wolfram's hypergraph formalism. These aren't just incremental tweaks to existing frameworks, they're full-throated reimaginings of reality's architecture, daring to ask, what if the universe's deepest structure isn't just hidden, but beautiful in a way we've barely begun to glimpse? Take Lissie's E8 theory, a riot of geometric elegance that tries to fit every fundamental particle and force into the symmetries of a single, intricate mathematical object, the E8 Lie group. Picture a snowflake but with 248-dimensional symmetry, its crystalline patterns encoding everything from quarks to gravity. Lissie's audacious claim that the vibrations and interactions within this hyperdimensional shape could generate all known physics with no extra dimensions or unproven particles required. It's a symphony where every note is a particle, every chord a force, and the conductor's baton is pure geometry. Critics argue the theory struggles to reproduce gravity's exact strength or explain quantum field theory's nuances, but its sheer aesthetic boldness has captivated mathematicians and physicists alike. After all, if the universe has a unified foundation, why wouldn't it be, at its core, stunning? Meanwhile, Stephen Wolfram's hypergraph approach flips the script entirely. Forget smooth space-time or even discrete loops. Wolfram proposes that reality is nothing more than a vast, evolving network of abstract connections, a cosmic game of connect the dots where the rules are simple, but the emergent complexity is infinite. In this view, particles are stable patterns flickering in the hypergraph's churn. Gravity is a statistical tendency of the network's growth, and even time itself is just the sequence of updates rewriting the graph's structure. It's reductionism turned up to 11, the entire universe as a computational process with no underlying physics beyond. These shapes transform into those shapes. Detractors dismiss it as computational mysticism, but Wolfram's team has shown startling successes like deriving relativistic effects and quantum behavior from hypergraph rewrites. The catch: the approach is so general it risks explaining everything and nothing at once, like a theory that can mimic any melody but can't predict the next note. What unites these seemingly disparate ideas is their willingness to tear up the rulebook and start fresh. Where string theory adds dimensions or loop, quantum gravity quantizes space, E8, and hypergraphs ask, what if we've been looking at the puzzle sideways? They remind us that unification isn't just about stitching old pieces together. It's about wondering whether the pieces themselves are illusions, shadows of something far simpler and wilder. Whether either theory survives rigorous scrutiny matters less than the doors they kick open. After all, the next great leap in physics won't come from polishing old paradigms, but from someone, somewhere, daring to imagine a universe unlike any we've ever seen. And that's where the real magic happens. From the delicate threads of loop quantum gravity to the cosmic holograms of string theory, these 30 theories reveal the breathtaking creativity of the human mind in its quest to crack quantum gravity's enigma. Each approach, whether it's the geometric ballet of twistors, the emergent chaos of entropic gravity, or the pixelated cosmos of causal sets, offers a unique window into what reality might be when we peer past the veil of our everyday experience. Some theories whisper of hidden dimensions curled into invisibility, others of space-time dissolving into quantum foam, and a few dare to suggest that gravity itself might be nothing more than a cosmic mirage. The sheer diversity of these ideas isn't a sign of confusion. It's a testament to how wildly unconventional the answer might need to be. Yet beneath all these wild variations, one unifying thread remains: the relentless drive to reconcile the colossal and the minuscule, to stitch Einstein's warped cosmos to the quantum whirlwind. Whether we're talking about black holes that store their secrets on 2D surfaces, universes built from vibrating strings, or gravity emerging from the churn of quantum information, the goal is the same: to find the single set of rules that governs everything from the birth of stars to the spin of electrons. It's a puzzle so profound that solving it wouldn't just rewrite physics textbooks, it would redefine our place in the universe. So which of these theories resonates with you? Do you picture reality as a hologram, a network of entangled qubits, or a cosmic Lego set snapping into place? Maybe you're holding out for a radical idea we haven't even dreamed up yet. Whatever your bet, the journey is far from over. Every unanswered question, every paradox is an invitation to think bigger. If you've enjoyed this dive into the cosmos' deepest mysteries, don't forget to subscribe and hit that notification bell. The universe has plenty of secrets left to spill, and we're just